questions in Lectureland, I'd be glad to answer them. Alright, so this is going to be chapter 13 of chemical structure and reactivity. So, just for any newcomers here who haven't been to my past lectures, I did do a really long pause on the series since I had some business to deal with. However, we do have the 13th chapter right here. And for you wondering what CSR even is, it's essentially just a really good British general chemistry textbook that I just randomly decided to do lectures on. And it's currently part of CODSLecture. So let's get straight into this. So the reason I put this specific slide, so this specific slide is called the start of a new era. The reason why I put that is because chapter 13, if you've seen my past lectures, chapter 13 is the first chapter of the going further section of this book. And in addition, this new section will continue on with what was going on in fundamentals. However, you'll get a lot more math, and therefore you're definitely going to get a better picture into topics that we've already discussed. Think something like thermodynamics, kinetics, or organic chemistry. And I also put a note here saying that in these next chapters, if you are seriously trying to go into something like thermodynamics or quantum mechanics, like the actual math behind this, while this book is a good starting point, it's still general chemistry. It's not going to be something like an expert book on quantum mechanics or electrodynamics. So please go and spend more time with actual specialized books if you're going to go deeply into these niche topics. So what exactly will this chapter talk about? So this chapter will focus on spectroscopy, which is a field that studies interactions between light and matter. We'll do some more studying on this later in chapter 18, where we'll use quantum mechanics to explain how spectroscopy works. And the whole reason why we do spectroscopy is because it allows us to read the various features of a molecule. Think of it as a molecular fingerprint. And in addition, spectroscopy is absolutely fundamental in your organic chemistry classes. As you can see, I have this old message right here saying that you have to do things involving spectroscopy after every reaction that you do. And that just goes to show how fundamental this field really is if you're trying to become an actual chemist. And so I want to draw back to what was said by the authors around think chapter 1. So in chapter 1, we were introduced to this technique known as X-ray crystallography. What exactly it was is that if we have a compound and we want to determine its structure, what we can do is we can take a crystal of that compound and shine X-ray light through it. And by getting a unique diffraction pattern, we can work backwards to figure out what exactly is the shape of this molecule. Now, the authors actually admit that X-ray crystallography is the best method to determine structure. However, one major issue is you need a crystal. When it comes to compounds such as proteins or biomolecules, it can be hard to obtain a crystal. And in addition, at times, we don't want to see how a molecule looks like in a crystal form, but in a solution form. And therefore, we're going to need another way to determine how exactly we can get the structures of these molecules. So the first technique that I wanted to show you of structural determination is known as mass spectrometry. So this is going to be a bit of history right here. So back in, I'd say 1800s to 1900s, we learned how to get ions of molecules, and we learned how to separate them using their mass to charge ratio. Say, for example, we have an ion that has a mass of 50, let's just arbitrary units, and a charge of +1. If we have a second ion with a charge of plus 2 with a mass of 100, they are indistinguishable from each other when we're looking at just the mass-charge ratio. And in addition, with mass spectrometry, we can observe a peak that is the same as the molecule, just with an electron missing. So say, for example, we have some sort of molecule that's neutral, right? Since it's neutral, there will be no mass-charge ratio. However, if we just knock off an electron, then there will be a mass-charge ratio, and it will just be the mass of that original molecule divided by 1. And in addition, in mass spectrometry, we can also see these things known as pseudomolecular ions, which involve some fragment of the original molecule that we're analyzing with another ion. So right here is a typical example of a mass spectrum. You can see on the vertical axis, we have relative intensity, and on the horizontal axis, we have the mass to charge ratio. Now, you can see that there are a lot of distinct peaks when we're looking at the spectrum. This spectrum is from caffeine. And these peaks are caused by different fragments being picked up by the detector in the mass spectrometer. However, if we're going to be talking about fragments and the mass charge ratio, we actually need to break up the molecule and ionize it. So the first method that we'll be using is known as the electron ionization technique. If I have some sort of molecule, then I can fire a bunch of high energy electrons at it. And these electrons will be removing the most loosely held electrons in the molecule. Take, for example, electrons in triple bonds or in lone pairs. Those are very easy to remove. And in addition, because we are firing these high energy electrons, this method of ionization is considered to be pretty harsh on the molecule. However, another method that we can use is known as chemical ionization, where instead of firing high energy electrons at our sample, we can get our ions or fragments from chemical reactions between the sample and some sort of reagent gas, including methane. Now, for more ionization methods, I want to talk about fast atom bombardment. As you can see, the name implies something similar to electron ionization, where we're getting some sort of particle being thrown at the sample. In fast atom bombardment, what we have is we have something such as glycerol and the sample. Using these two ingredients, we can create a matrix where the sample is held in place. And then what we can do is we can fire atoms of an inert gas. Take, for example, xenon or krypton. There's also another method known as MALDI, where we crystallize the sample first along with something else. And then we fire a high energy UV light beam onto it, and the ions are introduced to the mass spectrometer. Keep in mind that UV light is high energy, so it's going to knock some parts of the molecule off and create those ionized fragments. And finally, the most popular one that we use in terms of how we get these ionized fragments is through electrospray ionization, where if we have a solution of the compound, we can spray it through a capillary that's held at a very high electric potential. All right, so that's just mainly the introduction. I'll let y'all Karasparov, right? Did my answer your question well? But get the general gist? All right, nice. And log D, I'm clipping that for future purposes, all right? So anyways, for analyzing the mass charge ratio, we have two common methods, right? We have something known as a time of flight or a quadrupole mass analyzer. So in time of flight, what we have is an electric field that is applied. And so once we have those fragments in the mass spectrometer, that E field is applied, and it makes all ions move at the same speed. Remember that if we have an electric field applied on some sort of ionized particle, then it's going to move. There's going to be a force applied on that. We learned that from basic physics. Now, what we do is we take all these ions and we put them across a field. This can range from 0.3 to 1 meters. Now, since kinetic energy is directly dependent on the velocity, right? The lighter ions will have a greater velocity, and because they're traveling faster, they're going to hit the detector sooner. And then this detector will then give the mass-charge ratio. Now, as for a quadrupole mass analyzer, this was a bit tricky when I first learned it since I didn't know much physics. But in a quadrupole mass analyzer, we have 4 rods. And to shoot these 4 rods, we have an identical DC voltage with an applied frequency. Now, electric fields, they are created where ions with specific mass-to-charge ratios can safely travel. If we have any ions with unstable paths, they're just going to get neutralized. And by changing these voltages, we can scan and also separate these ions based on their mass-to-charge ratio. Fun fact, this can actually be used in conjunction with time of flight in what is known as tandem mass spectrometry. Hold up, let me check Lectureland real quick. Thank you for that clarification. That saved me a good bit of hassle there. So anyways, let's get to the actual setup with a mass spectrometer. So we can see that this is according to the textbook. We have a bunch of different labels for this instrument. So you can see label 1 is for a microsyringe. What this microsyringe is being used for is it's going to inject a solution of the sample into the mass spectrometer. And you can see that label 2 corresponds to a tiny charged capillary. Keep in mind that this charged capillary is used in the most popular ionization technique. Now, we can see that labels 5 and 6, they correspond to a quadrupole mass analyzer and a time of flight mass analyzer. And this is exactly what we're looking for in tandem mass spectrometry. And finally, at 7 at the back here, we have a detector that's going to detect our mass-to-charge ratios. Alright, now, I want to talk about something very interesting. So we all know that isotopes exist in nature, whether it be with chlorine, carbon with radiocarbon, hydrogen with deuterium and tritium. Isotopes exist all over nature. Now, these isotopes can have a specific effect on what a mass spectrometer will output. You can see that in this chart, we have 2 isotopes of bromine present, bromine 79 and bromine 81. And you can see because of this isotope difference, the mass will be changed. And therefore, we get 2 very distinct peaks that correspond, one corresponding to bromine 79 and another corresponding to bromine 81. So that is a very important thing to keep in mind whenever you're going to do mass spec. Not carbon 79, I said bromine 79. Alright. Anyways, here's a table that actually describes to you the relative atomic masses of these isotopes. And one important factor that I want you to check out in this table is the percent abundance. You can see that with something like bromine, right? The 2 isotopes of bromine are present in around, I'd say about 50-50 ratio. And so looking back at the graph, see, this vertical axis is relative abundance. We see a fairly equal peaks here that correspond to both of the isotopes. So that's a very important thing to keep in mind. Now, as for isotopic signatures, isotopic signatures are defined as the distribution of different isotopes of an element. And if we go back to this mass spectrum right here, I want you to keep that in mind. There are peaks present that they're 2 units away, which means that bromine has 2 isotopes that are 2 atomic units away in mass. And in addition, carbon can also exist, if you go back to the isotope table, as carbon-13. Hold up one second. And although carbon-13 is not as abundant as carbon-12, with only a 1.11% chance of existing, or just being as abundant as carbon-12, if a compound still contains n carbon atoms, then the ratio will be around 100 to n times 1.1. All right. Now, if a molecule has more than one atom that has different isotopes, so take, for example, chlorine, we can get a bunch of different peak intensity patterns. So we have 1,3-dichlorobenzene right here. You can see that we have 2 chlorine atoms attached to a benzene ring. Now, chlorine has 2 isotopes, chlorine-35 and chlorine-37. And you can see both atoms can be chlorine-37, both atoms can be chlorine-35, or one chlorine atom can be chlorine-35 and another can be chlorine-37. And this creates a much more complex mass spectrum than something like butyl-bromide, where we only have one atom that occurs in that actually has an impact because of its isotopes, which is bromine. Now, with a good mass spectrometer, we can actually measure the mass of an ion with crazy accuracy. We're talking about 5 parts per million or better accuracy. Now, we refer to highly precise mass spectra as high-resolution mass spectra. And because we have such a great level of detail, we can actually determine molecular formulas a lot easier. And this is an example of a high-resolution mass spectrum. And we can see this is for a ruthenium carbonyl compound. And so with this compound, the spectrum can be complicated as we have a bunch of different fragmented ions here. And in addition, we can see that these peaks all correspond to singly charged ions. But this specific region, if we zoom in on that, then this is triply charged, meaning that if we zoom in, we're actually going to get 3 distinct peaks. However, because they're triply charged, the differences in peaks are the 1/3 as much as those singly charged differences. Alright. Anyways, now, based on fragmentation, right, we can get complicated spectra for many different molecules. But regardless, even if we have these complicated spectrums, we still can have it serve as a unique fingerprint to determine substances in practice. So, I want you to just type in like Lectureland if you guys do any sports, watch professional sports, or like actually play sports. Like just type in Lectureland. Does esports count? No. But you know that athletes have to take drug tests. And fun fact, mass spectrometry is actually involved in those drug tests. So, using a technique known as chromatography, chromatography is just a simple way to separate different compounds in a mixture. We can actually identify certain molecules in, say, for example, blood or urine a lot easier. Now, This graph from the textbook is specifically of a sample of horse urine. And this bottom graph is from chromatography, and this top graph is the mass spectra of something specific, of a compound specifically known as nicotinamide, which is an actual drug. And so, because mass spectra function as unique molecular fingerprints, we can actually see in practice that we can identify these molecules. So just for a quick summary, I'll let y'all type y'all's questions in lecture land. Mass spectrometry relies on specific value known as the mass charge ratio. And in a mass spectrometer, we can have various ionization techniques that can produce different ions from an initial molecule. In fact, isotopes can play a unique role in how these spectra look, because they can create different peaks based on their relative abundance. Now, while mass spectrometers can create complex outputs, they can often help in determining the exact formula of a molecule or actually identifying that molecule. So, any questions so far? I'll let you type that. All right, no questions. All right, we'll keep on going. So, next I want to talk about something from chapter 2. So, in chapter 2, we learned that energy is quantized in these quantum shells when it comes to electrons. We have orbitals such as 1s, 2p, 3d, 4f, and all that, right? However, did you know that molecules can actually occupy quantized energy levels? We can see in this graph down here that there are discrete vibrational energy levels, electronic energy levels, and rotational energy levels. And in fact, this is going to lead us into our next topic about how exactly a molecule can transition between these discrete levels. So, if we're going to move a molecule from one energy level to another, we're either going to have it absorb some energy to make it move up to a higher level, or emit some energy in the form of photons when it goes down. Now, what we can do is we can fire some light at a molecule to make it go up a level. And in fact, to determine the energy of that photon when it hits that molecule and the molecule goes up, we can use the Planck relation. This is very easy, as we learned this in, I'd say, like basic high school chemistry. This relation states that the energy of a photon is directly proportional to its frequency. Or if you wanted me to say it mathematically, E is equal to h nu, where nu is the frequency. I know that people use F now a lot more often, but I'll still stick with nu. Now, as for the electromagnetic spectrum, of course we know that photons can be in different frequencies. When we go to something like the radio section of the EM spectrum, the frequency will be very, very low compared to something like gamma rays. And therefore, the energy will be less, since energy is directly proportional to frequency. Now, on the topic of frequency and wavelength and light, I want to introduce to you a new quantity. Now, this is known as the wave number, and it is defined as the reciprocal of the wavelength, or in other terms, 1 over the wavelength. Now, since we know that for any photon, if we multiply its frequency by the wavelength, we get the speed of light. Therefore, we can state that the wave number is also equal to the frequency divided by the speed of light. Now, the reason why we're going to need the wave number is going to be very useful in this IR spectroscopy. So, in this form of spectroscopy, what we're going to have is we're going to have IR radiation shining through the sample. And with the sample, it can absorb photons that have a specific energy. And then it can actually go up in these energy levels. Now, this means that transmission and absorption graphs are going to change whenever a molecule absorbs these photons. So if transmission is lower than normal, that means that the molecule is absorbing those photons and going up in those energy levels. And we can see we also have a traditional IR spectrophotometer, I guess that's what you call it. And in addition, we have salt windows, and we have places where we can actually hold these specific salt plates. Now, I wanted to talk to you about a molecule that I already have shown, which is carbon monoxide. So, if we go back to carbon monoxide, we can see that, of course, it has different energy levels, vibrational, rotational. We're going to primarily focus on vibrational here. And we can see that with this transmission graph, at different wave numbers just represent like the reciprocal of the wavelength of the photon that we're firing at the sample, right? We can see that there are going to be different dips in this transmission graph. And this is because at these specific wave numbers, the molecule is going to absorb the energy of that photon and it's going to transition to different energy levels. So imagine that we have a base vibrational energy level. If the molecule absorbs a photon and goes up one energy level, that's known as a fundamental. Now, if we go to something known as the second energy level, right? If we go from 0 to 2, then that's going to be our first overtone, 0 to 3, our second overtone, 0 to 4 is going to be our third overtone, and so on. All right. Now, IR spectroscopy relies heavily on vibration. Oh, by the way, channel for ICO, I don't know how you pronounce it. Let me check. I don't think so. But anyways, with vibrations, right? Because IR spectroscopy relies on vibrations, we can represent a bond vibrating with just two masses on a spring. And I actually gone to like the physics, like the math behind this, and it's actually pretty interesting to go out and derive the frequency of this vibration. So, no need to actually look at the derivation, but imagine that we have some sort of mass on a spring, like in the diagram shown to your right. The frequency of vibration is going to be equal to 1 over 2 pi times the square root of some constant known as the force constant. This is equivalent to the spring constant in physics problems over the mass. Now, for a bond has two atoms, right? You have one atom on one side and another on another side. What we can do is figure out, at which wave number does the molecule or the bond actually absorb these frequencies? And we can see, using the fact that the wave number is equal to the frequency over the speed of light, the wave number is equal to 1 over 2 pi c times the square root of the force constant over something known as the reduced mass. Now, the reduced mass is something that we use when we have a two-body problem like this. We have two atoms on a spring, pretty much. And we can see that the reduced mass is equal to the first mass times the second mass over the first mass plus the second mass. And the reason why we use this instead of just like one atom's mass or a second atom's mass or using both is because it allows us to treat this two-body problem as essentially just a one-body problem. And it just makes the process a lot more easy. All right. And we can see, if I pull up this video here, this is going to be of carbon monoxide. I'm not too sure about the actual simulation. I just found some website online. But if I play this video, you can see this bond vibrating at a very particular frequency. And in fact, we even are shown the wave number right here. All right. Yep, the genesis of IR. That's what you call it. Now, that was just for carbon monoxide. If we go to larger molecules, then of course their vibrations would be a lot more complex than those of simple diatomic. Now, we can split this motion into various normal modes. And here's an exact formula to determine how many normal modes there are for a nonlinear molecule. If we have a nonlinear molecule with n atoms, then there are 3n minus 6 normal modes. While if we have a polyatomic that is linear, there are going to be 3n minus 5 modes. So take, for example, sulfur dioxide. All right, this is going to be a nonlinear molecule that has 3 atoms. Now, using our formula 3n minus 6, we can plug in 3 for n, and we get three normal modes, which is actually what we see here in this simulation given by the authors of this textbook. And on the bottom, we can actually see the IR spectrum of sulfur dioxide, where we have specific stretches corresponding to these specific dips in the transmission graph. Now, as for how deep some of these dips may be, like I'm just speaking graphically here, we can see that the antisymmetric stretch creates a much deeper dip than something like a bend or a symmetric stretch. Now, what could be the exact reason for that? Well, the reason for this is because if we have some sort of stretch, right? On this side, we have symmetric stretch, we have an antisymmetric stretch right here. If we have a change in the dipole moment of the molecule, then there's going to be a much greater absorption peak or a dip in the transmission graph. And if we have an antisymmetric stretching mode for sulfur dioxide, well, of course, we're going to have a greater change in the dipole moment. And so this will create a greater absorption peak if we pull up the absorption graph than the symmetric stretching mode. Now, as for group vibrations, we can only say that with more complex molecules rather than diatomics, the resulting IR spectrum will be even more complex than before. So using the calculation for nonlinear atoms, if we take chlorobenzene, which has 12 atoms, there will be 3 times 12 minus 6, which is just 30 possible modes, which is a lot. And we can even see that being mentioned in this IR spectrum. And because of all these different normal modes, we get a pretty complicated spectrum to look at. Now, how exactly are we supposed to interpret these? So as shown in our previous slides, right? The frequency of stretching in diatomic molecules, it depends on the reduced mass. Because, of course, we model this vibration as a spring with just 2 masses. So logically speaking, since hydrogen is the lightest atom, it's going to result in the highest stretching frequency. Now, in addition, if we're going to be looking at IR spectra, we have to know which bonds are present in a molecule based on where these peaks or dips occur, as different types of bonds correspond to different regions and different wave numbers. All right, that's pretty much going to be like the end of my rant for now. I can answer some questions down in lecture land for now. Let me check. Well, some nonpolar molecules are IR inactive. Like, take for example, I don't know, N2, right? Nitrogen gas. If we have that, yeah, N2 or O2, no matter how we stretch that, there's going to be no change in dipole moment. But if we have something like CO2, CO2 is perfectly nonpolar in just normal form, right? However, there's going to be that antisymmetric stretching mode, and that will create a change in the dipole moment of the molecule, which means that CO2, which is nonpolar, is actually active in IR spectrum. Yep. All right, nice. Now, I'm not going to go like rant about these different stretches, at least for now, but here's a simple chart that you can look at to figure out where different stretches are located. So, from the region from what? Yeah, 2500 to 4000, we're going to get stretches that involve hydrogen. And of course, if we go back to what I said about, let me check. Yeah, we go back to this slide. Because hydrogen has such a light mass, logically, bonds to hydrogen would have the highest stretching wave numbers. And so, therefore, we see it in this particular region of an IR spectrum instead of here or here. Now, as we go down, we can see that we see triple bond stretches, double bond stretches, and various other single bond stretches. So, for example, a carbon-carbon bond in an alkane, or a carbon-oxygen bond in something like an alcohol. Now, let's go straight into this first region that involves bonds to hydrogen. Now, we use IR spectroscopy a lot in organic chemistry, of course. Now, since we're going to be dealing with organic molecules, no kidding that, of course, we're going to witness a lot of CH stretches. And in addition, even in preparation, if our sample doesn't contain carbon-hydrogen bonds, we can use something known as Nujol. And this is essentially something that we grind along with the sample to create something suitable for the IR for the machine. And Nujol is essentially pretty much hydrocarbon oil. And so we are going to see carbon hydrogen stretching in our IR spectrum, even if the sample itself, even if like the molecule itself doesn't contain any carbon hydrogen bonds. And that's just because Nujol is ground up along with that sample. So we're going to get to these stretches. Now, if I go back to this table here, we can see that based on the specific type of hybridization, like take for example, we have an sp3 carbon to hydrogen bond. That's going to correspond to something like the bond between carbon and hydrogen in methane. Now, if we have something, hold up. If we have something like an sp carbon to hydrogen bond, so take for example something like ethine. I think, yes, trivial name is acetylene, but if we have that carbon hydrogen bond in acetylene, we are going to get a higher stretching frequency. And matter of fact, if we go on to even more hydrogen bonds related to hydrogen, we can see that the stretches for nitrogen to hydrogen bonds actually occur at a higher frequency than carbon to hydrogen. I'd say right around here. And this IR spectrum is of a specific molecule known as aniline, which is just pretty much an amine group attached to a benzene ring. Now, this one was personally one of my favorite parts to read in the IR section, and that's because oxygen-hydrogen bonds are included in this particular region. Now, instead of something like a sharp peak with what you see with the sp carbon to hydrogen bond, we actually see a very broad absorption peak or transmission dip. And that's because if we have a sample, right, and the molecule has that OH group, so take for example like an alcohol that we have here, because hydrogen bonding is present throughout the sample, there will be interactions at many different lengths. And this exact hydrogen bonding, instead of a sharp peak, we get a smeared out signal, usually around 3,300 per centimeter. Yep. All right. Now, if we go from there into triple bond territory, this region, 2,000 to 2,500. Well, if I see something in lecture land, I mean, the purpose of using Nujal is because it acts as a suspension agent, right? And so this can be this allows for this mixture, right? Once we mold the sample with Nujal, it allows for that mixture to be smeared on those specific salt plates. Just a reminder for yourself, the broadness is due to the signal being an average aggregate for minimal. Each bond. Whether this affects the general depth of the peak. Yeah, the hydrogen bonding does affect the general depth of the peak. So yeah, you're pretty right there. So anyways, going on triple bond territory, this region will contain carbon triple bonds with oxygen, nitrogen, and another carbon. And in fact, if I go back to that spectrum of carbon monoxide, let's go back right here, we can see that I'd say like around 2000 2500, we get our fundamental frequency right here. And that actually corresponds to this triple bond territory. Now, I want to also talk about how dipole affects IR absorption peaks. So, imagine that we have a carbon-carbon triple bond and a carbon-oxygen triple bond. Oxygen is of course more electronegative than carbon, meaning that compared to something like a carbon triple bonded to an oxygen, if we have a peak, if we pull the absorption graph, the peak of a carbon that's triple bond to another carbon will be less prominent, and that's because there's not as much change in dipole. Now, we're going to go on to double bonds. So, carbon-carbon double bonds you see in a molecule such as ethene, they produce weak absorptions, and that's because there is no large dipole moment that's associated with them. However, do you know what has a large dipole moment? That's going to be the carbon-oxygen double bond. And this makes IR spectroscopy really useful when it comes to analyzing carbonyl compounds. And in fact, if we go to something like a straight chain alkane, right? If we have a ketone there, we're going to see an absorption peak at around 1715 per centimeter. Now, as for cyclic ketones, we can see right here in this diagram that if I keep on removing these carbons, right, then what will happen is that our absorption will happen at higher and higher wave numbers. Now, going on about the carbonyl bond, right, the carbon to oxygen double bond. We have seen in chapter 5, I recommend you watch that, this is pretty good. If we have some sort of lone pair from an adjacent atom with the carbonyl bond, then what can happen is that that lone pair can conjugate with that carbonyl bond, specifically with the pi electrons. Now, as you can see, in this carboxylate ion, we get a resonance structure because of the lone pair on this oxygen donating electrons. And therefore, the lengths of these two bonds are the exact same because of this resonance structure. So now the pi electrons are delocalized along three atoms. The first oxygen, the carbon that's double bonded to another oxygen, and the oxygen that's double bonded to carbon. So this not only affects the bond lengths present, but also the exact IR absorptions, because each bond has a strength and length that is between the double bond between carbon and oxygen and the single bond between carbon and oxygen. If we search up something like the nitro group, it is very similar. If we look at something like nitrobenzene, for example, we can see that the nitrogen is double bonded to one oxygen and singly bonded to another oxygen, which leads to resonance structure, meaning that if we take something like nitrobenzene and we throw that into the IR spectrophotometer, we get something that corresponds in the middle between nitrogen doubly bonded and nitrogen singly bonded to oxygen. In fact, conjugation does not happen just for like a ketone. If we have something like an amide where, I don't know, it's pretty much just a carbonyl fused with an amine, we can get even more resonance structures. And compared to a normal carbonyl bond, the wave number that corresponds to its absorption peak is lower. However, going back to ketones, remember sigma conjugation? This is essentially something where if we have sigma orbital, if we have electrons from alpha hydrogens, which are just hydrogens that are bonded to a carbon next to a carbonyl carbon, we can get sigma conjugation, also known as hyperconjugation. And this can make the absorption frequency of an aldehyde greater than a ketone. Since sigma conjugation with a ketone, there are going to be more alpha hydrogens, which decrease the absorption frequency. Now, I also wanted to talk about induction effects. So as we know, acyl chlorides, also known as acid chlorides, have a lone pair on a chlorine atom, specifically in the 3p orbital. However, we've already seen in chapter 11 that this 3p orbital does not overlap well with the pi system in the carbon-oxygen double bond. Regardless, that carbonyl bond is actually strengthened, with the carbon-chlorine bond becoming weaker. We can see that in the structure C, although it is a bit dramatized, that carbon-carbonyl bond will get stronger while that carbon-chlorine bond will get weaker, meaning that we're going to get absorption around 1800 per centimeter. And also a fun fact, for that structure C, that exact cation in the fourth resonance structure is known as the acylium cation. And we can prepare this using some sort of anion. Take, for example, BF4 minus. And in fact, this acylium ion, since it has that triple bond, we're going to see absorption in the triple bond territory, which is around 2,295 per centimeter. Now, I also want to talk about even more functional groups that involve carbonyl bond. So, both esters and carboxylic acids demonstrate strong absorption at wave numbers above that of ketone. And this makes sense considering that the lone pair of oxygen is delocalized and that the oxygen pulls electron density. Now, with acid anhydrides, we have two different carbonyls, meaning that we're going to get two different absorptions. Now, if we're going to look at the vibration frequencies or the stretching modes of an acid anhydride, what we're going to see is we get one mode where the carbonyls are moving in phase or just together, and another is going to be out of phase. Now, I just want to show you guys an example IR spectrum, but we can see that this is for aspartame. That's the stuff you find in Diet Coke. So we have this recorded in IR spectra, and we can see there are going to be specific bonds for this that correspond to like this amine group. There's going to be something for this phenyl ring, and in addition, because we have, let me check right here, because we have OH here, right? We have that alcohol group. We are going to get a really broad transmission dip there because of that hydrogen bonding interaction going throughout the sample. I also grabbed this quick table. You guys can screenshot it. I'll provide the PDF of this later. But this is going to be a quick table that shows different IR stretching frequencies. And it's pretty neat to memorize, just look at. And I honestly think it's pretty cool. So that's going to be the end of my talk, specifically on IR. We're going to enter NMR soon. So any questions in lecture land so far? Okay, let me check lecture land. Okay, no questions. All right. So this is gonna go into like a bit of quantum physics, but bear with me here. So this is gonna be called NMR. This is gonna be a new form of spectroscopy, and it's actually pretty cool. So NMR stands for nuclear magnetic resonance, and it's based off of a very important quantum property known as spin. Low-key, I want to say as undergrad, don't worry if you guys don't get NMR on the first try. Yeah, that's true. NMR can be really, really confusing for somebody, especially if they're going into this just straight without much experience with it or any idea of what spin is. And so, yeah, NMR can be a bit of a complex topic. I'm going to try breaking it down as much as possible in this lecture, though. So, I want you guys... Chapter 5? Yep, that's CSR. I have a lecture on that. So, recall that if we have an electron with a specific spin, spin is either plus 1/2 or minus 1/2 for an electron. The angular momentum is going to be equal to the square root of the spin times the spin plus 1 times the reduced Planck constant. Now, for NMR, we need nuclei that specifically have non-zero spins. And we can see in this table here, this quantity I, that's exactly what we're going to be looking for when we're going to figure out which atom's nuclei are going to have non-zero spins. So something like the hydrogen protium nucleus, right, which is just a pretty much proton, has a spin of 1/2. However, something like carbon-12 doesn't have any spin at all. So therefore, we can't use any compounds with carbon-12. We can't detect anything with NMR. Now, carbon-13, though, does have a non-zero spin, meaning that it's viable for NMR. I also do want to state that spin is defined as pretty much quantized angular momentum. If you do go into the math behind this, which I'm pretty sure we will do in chapter 18, is going to definitely be a bit of an adventure. And in addition, if you're going to go into stuff like the Dirac equation and all that, it can get pretty complex, but it is actually pretty cool. Now, when I first read about NMR, I thought, this name sounds similar to MRI. And if we look at what MRI stands for, magnetic resonance imaging, we can actually draw some connections between it and NMR. So, Magnetic resonance imaging, where they put you in the hospital and they make you remove all the metal off your body, that relies on a pretty large magnet with a really good magnetic field strength, which is around 1.5 to 3.0 Tesla. Keep in mind, the Earth's magnetic field is way, way smaller than that. Now, this big magnet essentially aligns all the protons in your body. And once a radio wave hits your body, the protons are knocked out of their organized arrangement. However, once you turn off that radio wave pulse, your protons quite literally release EM radiation. So I was thinking about this like when I was first reading how MRI works. Like your brain quite literally releases electromagnetic radiation that's picked up by a detector. And so as we get into this, NMR is actually just pretty much MRI for molecules. Now, I want to talk about an NMR signal. Now, the NMR signal is essentially just a measurable radio wave that is generated by atomic nuclei. Now, with these atomic nuclei, it relies on the same principle as MRI. We subject it to a magnetic field, and we send radio wave pulses that make it release EM radiation. Now, the two most common nuclei that we're going to look out for NMR is carbon-13 and hydrogen-1, or just protium. Now, if we're going to look at the local electron environments around these nuclei, we're actually looking at something very important here. And the reason for this is because if we subject these nuclei to an external magnetic field, then if we have electrons around it, then the nucleus will shield it. I mean, the electrons around the nucleus will pretty much shield it, making these opposing magnetic fields. So therefore, if we have less electron density around some sort of nucleus, then that nucleus is less shielded. And therefore, we're going to get a greater frequency of resonance that's going to be picked up by the NMR detector. Now, NMR magnets can differ in magnetic field strength. I myself have seen an NMR machine, but I do know that there can be different frequencies for these machines. Now, because of this, we never actually care about the absolute frequencies of the emitted EM radiation. Instead, we utilize a reference compound, and we express the chemical shift using the formula below. So delta is going to be our chemical shift in parts per million, and it's going to be equal to 10 to the power of 6 times the difference in frequencies divided by the reference's frequency. Therefore, if we have an NMR machine that runs at 700 megahertz, then 1 part per million corresponds to a difference in frequencies of 700 hertz. Now, this is going to be a pretty important reference compound known as tetramethylsilane. Essentially, what tetramethylsilane is it is a volatile compound made of carbon, hydrogen, and silicon that is utilized as a reference for both proton, which is hydrogen 1, and carbon-13, NMR. And the reason why this is such a good reference is because the carbon and hydrogen atoms are in the exact same environments. Their electron distributions are exactly the same. And so therefore, we're going to get a single peak instead of a bunch of different complex peaks, which makes this really useful as a reference. And in addition, since silicon is actually less electronegative than carbon, electron density is going to be pushed out to the methyl groups, which will create a more distinct NMR signal if we compare it to other compounds out there. So that's going to be like the end of the 10 slides. Yep. We can have some questions in lecture land. Y'all can just type that out. I'll be happy to answer them. Alright, no questions so far. I'll keep on lecturing. So, when it comes to identifying the number of peaks that you're going to get in your NMR spectrum, whether it's for carbon or proton NMR, it's important to recognize that there are going to be carbons in different electron environments with different electron densities. So take, for example, this first compound, 3 non-unknown. We're going to be doing carbon NMR spectra on it. So we can see that there are going to be 9 exact NMR peaks. And that is going to be because each carbon is going to have a different electron density around it. Now, as for something like 5 non-unknown, that molecule is symmetrical, meaning that we're going to get 2 carbons in, say, for example, environment number 3 or in environment number 1. And so, therefore, determining how the environment will look around a carbon is very useful for looking at how many peaks we're actually going to get. Now, I also wanted to talk about integrating peaks. So, in an NMR spectrum, those peaks aren't just a single spike. They have some area under them, and the area under each peak is directly proportional to the number of hydrogen atoms in that specific environment. You can see in this proton NMR spectrum that we have 4 different environments here. And we can find the area under these peaks to figure out, relative to other environments, how many hydrogens this specific environment can have. Benzene as a reference? Yeah. Stereochemistry hater is correct. Because if you're using benzene as a reference, good luck actually testing anything that's organic or that's aromatic. Good luck actually trying to do that. Tetramethylsilane is just the method for that. Now, here are also some chemical shifts that correspond to different bonds involving carbons. So we can see that the more downfield a shift is, downfield just means that it's going to be greater ppm. We're going to enter from, instead of something like a tetrahedral carbon, we're going to see something like an sp2 carbon, or we're going to see something like a carbonyl carbon. And this is just a pretty neat reference to have up if you're going to be interpreting these spectra. Though I do know that there are computer programs that can handle NMR for you. Now, if I go back to some of these original NMR spectrum, like take for example carbon-13, we can see that there's a specific peak associated with CDCl3. CDCl3 is just deuterated chloroform. And well, it's just a very common choice for both proton and carbon NMR. In addition, heavy water and DMSO are also solvents that are used in NMR. The exact reason why we use deuterated solvents, deuterium is just an isotope of hydrogen with a spin of 1, is because if we're going to be doing proton NMR, there will be no proton NMR peak. And in addition, it ensures that the NMR machine will be more stable. So, if I want to talk about coupling, coupling is essentially a phenomenon that happens when we have one nucleus. Take, for example, the carbon-13 nucleus and some other nucleus that's attached to it that has a non-zero spin. Take, for example, the fluorine-19 nucleus. This creates a splitting in peaks. And we can see that for normal acetic acid, there is no splitting of peaks. But for something like fluoroacetic acid, there's going to be coupling occurring with the carbons and the fluorine nucleus. And that's going to create those doublet peaks that we see right there. So when I first look at this diagram, actually, I thought, wait, carbon-13 has a non-zero spin. If we have acetic acid, then why is there no noticeable coupling? Shouldn't the carbons couple to each other? And the reason for that is because the chance of carbon-13 occurring in nature is 1.1%. If we have two carbon atoms, the chance that we're going to have two carbon-13 nuclei is going to be 0.011 squared, which is really, really small. And in addition, identical nuclei don't couple. Now, we can see that with these split peaks, there is a constant difference between these peaks. And this difference is known as the coupling constant measured in Hertz. Now, the coupling constant is also called the J value. And this J value is consistent with, take for example, these peaks, for example, some peaks right here. Coupling is a two-way process, where if we have nucleus A splitting the peaks of nucleus B, then nucleus B will be split by the J value the exact same way. In addition, when we're looking at split peaks, we can see that some of these peaks have a greater intensity than others. And for that, we can use Pascal's triangle, where we see that if we have some sort of split peak, take for example a triplet, then the central peak will be 2 times as intense as any of the other peaks. Now, another question that I had when I was looking back at this NMR spectrum was, why doesn't the carbon nuclei couple with a hydrogen nuclei? Hydrogen usually occurs as just, the hydrogen nucleus is usually just a proton most of the time in nature. However, most NMR for carbon-13 is recorded in such a way that there is no proton coupling. Proton coupling does happen, it's just that we omit it out of our data, and this is known as broadband proton decoupling. And the way that this works is essentially the sample is going to be hit with radiation that will cause the spin states of the protons to flip between their exact states. And we can see that we even get these satellite peaks from splitting. Now, what I described when I talked about fluoroacetic acid was coupling between the carbon-13 nucleus and the fluorine-19 nucleus. However, what if I take fluorine and replace it with something that has a non-zero spin greater than 1/2? So say, for example, I go back to like boron 11, right? That has a spin value of 3 halves. However, one issue is we're not going to see any noticeable coupling, and that is because of a process known as relaxation, where if we have a nucleus, based on the spin, there are going to be different spin states that rapidly interconvert. And therefore, our peak will collapse into a singlet because of this relaxation process. Now, we're going to get into my least favorite section of this chapter, but this is going to be proton NMR. And the reason I say that this is my least favorite section of the chapter is because proton NMR is, of course, noticeably harder than carbon NMR. You're going to have a lot more business dealing with something such as coupling constants, shifts, and also different environments. And you can actually see that in these specific spectra. We can see that some of these peaks don't follow what Pascal's triangle says. And we'll actually explain this in the next slide right here. So we can see that for this specific compound, acrylonitrile, we have 3 different hydrogens. We have hydrogen A, hydrogen B, and hydrogen C. Now, an issue, if we look at hydrogen C, is that the intensities just look weird, right? It looks like we're having a house roof and it's just slanted. And that's because the nuclei's energy levels are mixing. And this specific occurrence is known as the roofing effect. However, let's disregard that for now, and let's talk about more coupling constants when it comes to proton NMR. So, in the spectrum of acrylonitrile, right? Past me would have said, I see that hydrogen A and hydrogen C, they're trans, but hydrogen B and hydrogen C are cis. So the coupling constant for hydrogen B to hydrogen C should be greater, right? Wrong. And that's actually explained by something right here. So coupling is actually through bond interaction. And the trans coupling in the alkene has the largest coupling constants. And in fact, if we're going to be coupling over 3 bonds, like we have here with these hydrogen nuclei, the size of the coupling constant is dependent on something known as the dihedral angle, which is an angle between 2 specific planes. Imagine that we have one nucleus of element X and another of element Y. If we have a plane that contains the carbon X carbon X bond and the carbon-carbon double bond, and we have another that contains the carbon-carbon double bond and the carbon Y bond, then we can determine the angle between those two to look at the exact value of the coupling constant. And this, in fact, is in something known as the Car-plus equation. And we can test this on a specific molecule right here, cyclohexane. Now, this is because in many molecules, single bonds rotate freely. However, in cyclohexane, the geometry is largely fixed. We're going to be stuck in that chair configuration, meaning that both dihedral angles and coupling constants will be predictable. I also wanted to talk about something known as vicinal coupling. So vicinal coupling is what you saw with these hydrogens coupling in acrylonitrile, where we need 3 bonds, but geminal coupling only needs 2 bonds. So that is something that's going to be pretty useful if we're asked on it, like for an exam. And in addition, I wanted to show you just an example proton spectrum for sort of a cyclohexane looking compound in chair configuration. This is called 4-phenyl 1,3-dioxane. We can see that there's a peak corresponding to the solvent, but we also see multiple split peaks and a little bit of roofing. Now, there is one major issue when it comes to proton spectra, and that is, let's take for example, this specific compound known as pentane nitrile. We just have nitrile group attached to like 5 more carbons. You know what's 4 more carbons. What's 4 more carbons going to do? But as we keep on adding carbons, signals are going to start to merge. And especially in dodecanitrile, we're going to have so many carbons that there's going to be a lot of coupling and the signals will just straight up fall into each other, which creates these unresolved and confusing spectra. And so I also wanted to talk about proton shifts. So chemical shift depends on electron density, this local environment around nucleus. Now, this of course means that the local magnetic environment matters. However, predicting the shifts exactly is not going to be easy. For example, if we have the delocalized pi system of benzene, right? We are going to get these ring currents if we have an applied magnetic field, which creates a more downfield shift. However, with a linear pi system in something like an alkene, such as ethene, we are going to have a less downfield shift and a bit more upfield compared to something like benzene. And finally, I want to talk about exchangeable protons. So, as you can see in this exact, let me see if I put this somewhere else. Yeah, proton NMR shift. There's nothing about hydrogens being attached to nitrogen or oxygen, and that's because their chemical shifts can vary over a wide range of values. And in addition, these peaks can be often more broad than carbon-hydrogen signals and are influenced by hydrogen bonding. In fact, there's a certain test that you can use with heavy water, which is just deuterium oxide, where if you take that sample that contains protons bound to either either nitrogen or oxygen, that was a typo, those signals disappear, and that's because the proton is being replaced by deuterium, which does not appear in proton NMR. So that's going to be a pretty neat chart that shows like different shifts based on like where a proton is in the molecule. And to finally sum it all up, here are going to be the 4 different points that I want you to remember. So first off, with mass spectrometry, what mass spectrometry does is it just looks at the mass to charge ratios of molecules and their fragmented ions. Second off, light from various regions of the EM spectrum can be used to achieve different goals with the atoms and molecules. Third, IR spectroscopy looks at the vibrations that happen within molecules, which helps to identify functional groups. And finally, NMR depends on the chemical shifts based on various environments of nuclei. And so, for a sneak peek into chapter 14 of CSR, the next chapter will talk about even more organic chemistry. If you remembered chapter 11, we talked about the basics of organic chemistry, like hydration, creating acetals, all of that. But this one's going to focus a lot more on stereochemistry, which deals directly with the 3D orientation of atoms in an organic molecule, and how exactly this will affect the reactivity and properties of that molecule. Take, for example, limonene, which in one configuration smells like orange, but in another configuration smells like pine. And so that's the lighthearted way to show how symmetry and stereochemistry can go far in the world of organic chemistry.